Okay, so today we're going to go ahead and discuss how to find work for both constant forces and especially for non-constant forces, for varying forces. So let's just do a little example together first. So let's say if you apply a 30 Newton horizontal force to push a book 2 meters across a table. So how much work do you do? So we know that our equation for work is force times displacement. And feel free, if you need a refresher on this, watch my other video. So I know the force is 30 newtons and it's moving in the same direction the force is applied, so it'll be positive work. So this is going to be 60 newton meters, or you could say 60 joules. Cool. Let's go ahead and make a force versus displacement graph for the situation. So we know here is force, here is our displacement. The force is 30 newtons always, and that happens over a span of 2 meters. Cool. And again, this constant force, it means it's always 30 newtons the whole entire time. At 0, 1, 2 meters, we're always at 30 newtons. Cool. So let's think about that. How can you find the work done from a force versus displacement graph? So I want you to pause this video, puzzle over that yourself, and then check back in. And again, we're talking about like how graphically, like using either slope, shapes, whatever it is, can you find work done? So let me look at this. It looks like to me we can find the good old area. So we can make this into a rectangle and we can essentially get the work. So work will essentially be the area under the curve of a force versus x graph. So let's go ahead and look at it. So we know that this side right here, the left-hand side, is going to be 30 newtons. We know that the base is 2 meters. And if we want to find the area, we just multiply base times height, which is the base is 2 meters, the height is 30 newtons, so we are left with 60 newton meters. And again, I always use the units to help me out with this. So work is the area under force versus position graph. What we can do for this is how we can write this using our ideas of calculus. Area is going to be the integral. So work is the integral of essentially it's like f times x, but we're doing f with respect to x. So we're taking the area of a force position graph, the area under a curve. So this equation will always work no matter if the force is constant or not constant. In this case, we went ahead and used it for a constant force F, but we might use it for non-constant forces overall. Cool. And I'll also just write as a reminder, again, the area under a curve, we know that is called the integral of a force versus x graph. So let's go ahead and solve a couple example problems together using this new formula. Okay. So let's go ahead and do an example together. So we did a lab as a class involving Cook's law. So we hung a spring, attached different weights or masses to it, measured the force of the spring, and then also the displacement of the spring, and then made a little graph. So it looks something like this. So let's go ahead and calculate the work done by the spring from 0 to 1 meter. So let's look at it. From 0 to 1 meters is going to be from here to here. We just learned that work is going to be the integral of f dx, or the area under a curve of a force versus displacement graph. So that is just going to be this whole area. So we know that the height is going to be 80 newtons, the base is 1 meter, so the work is going to be, it's a little triangle to find the area, so it's 1/2, base is 1 meter times 80 newtons. So that is just going to be 40 newton meters, or we could say 40 joules. Awesome. Okay, let's go ahead and look at another point. So calculate the work done by the spring from 2 to 4 meters. So I'm going to use a different color for that. So from 2 meters to 4 meters. So we're going to need this whole entire area. I'm not that good at finding the area of things that aren't rectangles or squares or triangles, so I just love to split things into triangles because this looks like a trickier one. I'm going to split this into two shapes. So I have this triangle up here, and I have this good old rectangle like thing down there. So the top, let's go ahead and see, what is the area of the top? So the base is 2. So to go from 2 to 4, we have 2. I'll go ahead and write that down. The base is 2 meters. The height is 160 to 320, which is, oh my goodness, if I can write, silly. So 320, sorry, 160 newtons. So we do 1/2 base times height on this using the area of a triangle, and we get 160 newton meters, or 160 joules for the top triangle. Now let's go ahead and look at the bottom rectangle. So we know the height of this rectangle is also happens to be 160 newtons. The base is going to be 2 meters. So the area is going to be base times height, which is 320 newton meters, or 320 joules. So now let's go ahead and just add it all up. So we know work is going to be the sum of all that area. So that's going to be what? 320 plus 160, which will give us 480 newton meters. Cool. One last example to think about. If we have, let's say, a force versus position graph kind of like this, and let's say we have 10 newtons, let's say this is 2, let's say this is 4, let's say this is -10. We go from here to here, here to here. I didn't really draw that to scale very well, but if we were to find, let's see, and we were to find the work, I won't even worry about units, that was lazy. So we would need the work of the above, work of the below. In this case, the work of the above would be what? 10 times 2 divided by 2, so that would be positive 10 newton meters, or positive 10 joules. Below we have 2 by -10, so that's what area? 2 times 10 divided by 2, but then we can't forget it's negative, so -10 newton meters. So in a case like this, the work would just be 0 newton meters, because the area above and below the x-axis cancels out, so the net work would be 0 joules. Awesome. Thanks for watching.